Hello and welcome to a video on problems involving reaction pathways. So in this video, we're going to be just covering how to solve problems involving reaction pathways. We have a separate video on identifying products, so wait for that. We're going to be covering a couple of things in this video. So the first two items, I'm going to be giving you a sheet on all the reactions that we've covered throughout these videos or this video series. The second thing we're going to cover is a really high yield sheet that you can use when solving problems or just use to revise in general. We're going to be going over some easy problems that you can expect, especially in Year 12 chemistry exams, and then some harder problems where teachers might try and trick you up. So here we have a very, very broad mind map of all the reactions that we've covered in the last couple of videos. It might seem really hard to interpret, so I'll take you through it. Essentially, what we're doing is, for Year 12 chemistry, you're going to get questions where you're asked to make, say, a haloalkene. I'll use the red marker here. Say haloalkene, and you want to make, you're given the haloalkene, and you're asked to make, for example, a ketone. So essentially, you'd use this mind map, and it's kind of like a puzzle. So you're tracking the path to get to the ketone in the shortest way. So the first thing you'd want to do is add sodium hydroxide to the haloalkene to form this alkene here. So sodium hydroxide in an ethanol reflux. And then it's going to want to undergo a secondary oxidation reaction to form the ketone. So that's really how you interpret it. Now, I don't recommend you use this diagram as it's very, very complicated. And quite hard to memorize and interpret, but there are some key takeaways that you can take home. So there are a couple of high yield takeaways that you can take from it. In the next slide, I have a more simple mind map that you can use, especially when solving questions or revising, and that's much better because it's so much easier to interpret. However, this mind map does have its advantages. I wouldn't recommend revising off this because it's information overload and there's a lot of information on this page. However, I'd recommend using it to, if you get a chance, knowing how to make or how to interact in between the nitrogenous compounds, which is actually not kind of understated in most of the mind maps that you're going to find. I'd recommend supplementing this with the video that we made on amines, amides, and nitriles, because that's also a good video going over the ins and outs of all the reactions. However, if you just want a brief high yield understanding, I'd recommend memorizing at least that bottom right corner of the map. Another good thing that this map is good for is the legend down the bottom. Although it's really rare that you're going to be asked what type of reaction. So say they ask you to form an alkene from a haloalkane, right? So that's an example of a nucleophilic substitution reaction, signified in the legend by the blue arrow here. Although it's not integral that you know the mechanism and how the reaction actually proceeds, it's actually quite important you know what reactants or what catalyst is used and also what type of reaction it is. I think that's quite important to understand. As well as knowing what type of reactants you need to get in between these reactions, because I feel like it's important, it's also worth knowing a couple of strong oxidizing and a couple of strong reducing agents. So a strong oxidizing agent, or an example one, would be potassium permanganate in dilute sulfuric acid, and you'll see this pop up a lot in the questions that we're going to do. And a strong reducing agent would be sodium aluminium hydride in a dry ether. So those are two examples of two common catalysts that are going to come up in your Year 12 chemistry syllabus. On the slide, I have a mind map that is much, much easier to interpret and use in your Year 12 chemistry syllabus. Also, due to the resolution changes, both the mind maps might look kind of blurred on the video. I'd recommend popping up the slides because they're in much better quality on the slides and you can zoom in and screenshot and go from there. However, this mind map is much, much easier to use, especially in a Year 12 chemistry setting, and we've designed it specifically for you guys to use when solving problems. Obviously, in an exam setting, you're not going to be allowed to use this mind map. You can only use the formula sheet and anything else that your school supplies to you. But in an external exam setting, you'll only be getting the formula or data sheet, depending on which state you're in. However, to get an understanding of these reactions, or to be able to answer questions, I'd recommend using this mind map. You don't have to strictly memorize this mind map or even the one on the previous page here. I'd recommend just doing a lot of practice questions using either of the mind maps that you're more comfortable with. I'd recommend this one because it's just easier to interpret, but if you like the look of this one and you like the complexities of it, whatever floats your boat. So as I was saying, I don't recommend completely memorizing every single reaction step and every single reaction mechanism, because that's just a huge colossal waste of time. I would recommend more so doing a lot of questions using this mind map, and then slowly starting to do questions without the mind map and starting to memorize it that way, because I think practice makes perfect. Now, to go over how to actually use these mind maps and properly answer these questions, we're going to be going over 5 problems. The first 2 are quite straightforward and just a warm-up exercise to get your brain working, and also just to give you some practice on how to use the mind maps that we've created. However, the next couple are more exam-style questions that you can expect in your Year 12 chemistry exams. So the first problem states that devise a reaction pathway to form propanol from propane. So it's really important to read the question. It's not asking you to form propane. It's asking you to form propanol from propane. So you're starting with the propane. In effect, we're making a alcohol from an alkane. And that's what we're going to look for in the map. So on the map, we're going to look for the alkane first, and then we're going to look for the alcohol. Now, to get from there's, as you can see, there are actually a couple ways we can actually make the alcohol. So in an exam setting, if you were to go either way, so you can obviously go you can go this way, or you could go that way. In an exam setting, if you set out your working right, you write the formulae for each of the reactants and products, and you write the arrows and you write the catalyst required, you get 4 marks, whichever way you go. However, we're going to pick one. We're just going to pick the most simplest route, and that would obviously be this one down here. You just have to do less things. So my plan is you can also write a reaction to form the alkane, then the alkene, and then the alcohol. Also, alcohol and alcohol are interchangeable. But what I'm going to do is go from the alkane. I'm going to make a chloroalkane by chlorination and UV light. That just means UV light or energy. And then react it with a strong acid to make the alcohol. So in the solution, that's very similar to what actually happens. So we have our propane here, and then it undergoes a bromination reaction in the presence of UV light to form 1-bromo propane. And then, so in the presence of sodium hydroxide and a bit of heat, on a reflux preferably, we form the alcohol, which is propanol. So in this way, we get propanol from propane. Now, one thing, if you're keen in the eye, that you might have observed is bromine. Where did that come from? Because in the previous slide, we have alkanes forming chloroalkanes forming the alcohol. However, why have I got bromine here? What I wanted to show you is this is just a So that is just an example of a halogenation reaction. So you could have any halogen here. So it could be chlorine, it could be bromine, it could be iodine, so on and so forth. This reaction here is unchanged regardless of which halogen you have. To recap this reaction, I'd recommend you revisit our video on reactions involving alkanes, where we explore this concept in a little more depth. However, if you'd like to just keep it simple, then if you want to make it a chlorine, it doesn't matter. However, in this case, I just want to show you that you could theoretically use any halogen and you get the same result. So in the second reaction, we're asked to devise a reaction pathway to form propyl ethanoid from propene and ethene. Now let's break down what propyl ethanoid is. So as you can see, we've stepped up the difficulty a little more, so it's a little less straightforward. So propyl ethanoid, if you recall from the way we name esters, the prefix in front of the O8 part is the carboxylic acid. And the thing with the YL suffix is the original alcohol. And remember, carboxylic acids and alcohols combine to give you the ester. So we need an ethanoic acid, and we need a propanol. Because as you might remember, carboxylic acids and alcohols combine to form esters. And the length of the alkyl chains of each of the carboxylic acids and the alcohols stays consistent to make the final ester. However, we're in a bit of a trouble. We haven't been asked to make propyl ethanoid from ethanoic acid and propanol. We've been asked to form propyl ethanoid, from propene and ethene. So we need to devise two sets of reaction mechanisms. So firstly, we need to make this into propanol, and then we need to make this into ethanoic acid. And then these two will combine to give you propyl ethanoid, which is our final product in reflux. And that's exactly what we're going to do in the solution. So we're starting with propene and ethene, which are both alkenes, right? And we need to make an ester, which is all the way down here. Now, one of these, we're gonna make both of them into alcohols first. So we're starting with propene and ethene. The ethene needs to become ethanoic acid, and the propene needs to become propanol. These two will then combine to give you propyl ethanoid. So let's make propene into propanol first. So it's going to undergo a hydrolysis reaction in the presence of water and a weak acid. So we have phosphoric acid here, and you need a bit of temperature, so 300 degrees Celsius. So that's what we're going to do here. With ethene, there's a couple of ways you can go about it. So we'll probably do the same thing. Form ethanol. So ethene reacts with water and the weak sulfuric acid under 300 degrees Celsius to form ethanol. And then it undergoes an oxidation reaction with potassium permanganate, or the permanganate ion, to form the carboxylic acid. Then propanol and ethanoic acid under reflux will form propyl ethanoid. So here's exactly that represented diagrammatically. So we'll work through it systematically. On the top, we have one propene. It undergoes a reaction in the presence of water and a dilute acid. In this case, we had sulfuric acid. If you've got a keen eye, you might question, where did the sulfuric acid come from? Because in the previous example, we were talking about phosphoric acid. And that's where I want to really dial home this point about these reactions. It doesn't really matter what conditions you use, just memorize or remember the fact that it needs to be, if you're going from an alkene to an alcohol, it just needs to be in the presence of water, a dilute acid, whether that be sulfuric or phosphoric acid, and heat. And I'll just put heat down the bottom here as well. Now, we go from propene, or one propene, and we formed one propanol. So step one done. We formed our alcohol. Next, we need to get from ethene to the carboxylic acid. So that's exactly what we're going to do. So we have ethene here. Once again, in the presence of water and dilute sulfuric acid, could also be dilute phosphoric acid, we form ethanol. Now, ethanol and one propanol reacting together is useless to us. we need a carboxylic acid and an alcohol reacted to form our final ester. So we need to get this ethanol into an ethanoic acid somehow. Like I said, what's going to happen is it's going to undergo this reaction here in the presence of the permanganate molecule, as well as in the presence of an acid. The next step, ethanoic acid and propanol under reflux or in the presence of concentrated sulfuric acid form the ester of choice. So this is propyl ethanoid. You could also write concentrated sulfuric acid, or you could write and then on the bottom of the arrow you could write reflux. But either way, both answers would be accepted in an exam setting. So we're going to be stepping up the difficulty with the problems we have. So problem 3, 4, and 5. So these are more exam style questions that you can expect. So in an exam, you'll probably be given a large schema or diagram such as this. And then, so say you start at A, and then it undergoes a reaction to form C, which then forms D, and so on and so forth. So that's what you'll get in an exam. And then different parts of the schema will be blurred out. So in this case, it's A, B, C, D, E that are blurred out, and also reagent X. So that's kind of what you need to find in an exam setting. Moral of the story, practice going from not knowing what the individual products are to the reactants, and also practice memorizing or learning how to solve problems with where you need to find the reagents as well. So we need to find a couple of things. So we'll start with compounds A and B. So if we flick back, both compounds A and B have the empirical formula C4H8. Now, C4H8 is in the form CnH2n. You might recall in our video on alkenes that this is in the form or the formula for an alkene, or an alkene with 4 carbons. So this is butene. Now, compound A and compound B are 2 forms of the same compound with potentially different structures, because if they were both the same compound, this would also be compound A. So we know that compound A and B have the same formula, but they have potentially different structures, which sounds like they might be isomers of one another. Now, we also know that compound A and B are both butene. Now, if I draw the structure for butene, you can have this, the double bond in the first position, or the double bond in the second position. So compound A and B are 1 butene and 2 butene. Both these have a formula of C4H8. So in this way, we've solved A and B. So the next thing we can cross off our list is A and B. So the next thing we need to find is C. So we know A is 1 butene and B is 2 butene. Now, in an exam setting, if you were to say that B was 1 butene and A was 2 butene, so essentially the other way around, you'd be marked correctly because they're isomers of each other. They have the same formula. It doesn't matter which way you put it. However, the one thing that they both have in common is that when they're both heated in the presence of dilute sulfuric acid, they form compound C. Now, this is where doing a lot of these questions comes in handy. So A and B are both examples of alkenes. From previous questions, when alkenes are heated with dilute sulfuric acid, they form alcohols. So you can have a guess that compound C is probably going to be an alcohol of some kind with 4 carbons left, because we can't just make carbons out of nowhere. If butene undergoes a reaction with dilute sulfuric acid and some heat, it's going to form probably some kind of butanol, right? Okay, so we've worked through it systematically and we're actually on our way. So we've done A, B, C, and we'll get D soon. So we know that C is butanol of one kind. Recall that A and B are either 1 butene or 2 butene. So C is either going to be 1-butanol and or 2-butanol, and we'll have a discussion on what type of butanol it is in the near future. However, let's focus on compound D for now. Now, although this empirical formula here doesn't really tell us too much about what type of compound D is, this reaction mechanism actually tells us a lot about what type of compound D is. So, you may recall from the mind maps that that is a oxidation reaction that's occurring. So compound C is oxidized to form compound D. Now, whenever you see that dichromate ion in reflux in the presence of an acid, you should immediately think oxidation. So if you see Cr2O7 or you see permanganate, so MnO4-, immediately think oxidation. Now, can you have a guess if alcohols undergo oxidation, what type of compounds do they form? So we've got a couple of reactions happening now. We know, we'll tick off the ones we know. We know A and B are either 1-butene or 2-butene. We know C is butanol of some kind. We don't know if it's 1-butanol or 2-butanol. We'll discuss that later. Let's just focus on putting some answers down. So we need to find D. Now, we've got two pieces of information. So we know C is butanol of some kind. I'll write that here. We have an empirical formula for D, which is C4H8O. That doesn't really tell us too much. However, what is the giveaway for D is this reaction mechanism here. So we have reflux. So compound C is heated under reflux. That's kind of how you interpret that information. Compound C is heated under reflux in the presence of the dichromate ion in a slight acidic kind of atmosphere. It'll give you compound D. Now, what compound D is quite interesting. And that is kind of where the original mind map with the really complicated one, the advantages of it, really come to fruition. So this is an example of a reaction where we will need to consult this huge mind map here. So we've got butanol, which is the alcohol here. And I'd like to bring your attention to the table on the top right. Anytime you see dichromate or permanganate in acid reflux, you should immediately be thinking oxidation. Immediately. So oxidation immediately. Oxidation is signified by the yellow arrows. So let's start at the alcohol and follow the yellow arrows down. So we've got two examples here. So that's one yellow arrow, or amber arrow, sorry, not yellow. So we can either form an aldehyde or we can form a carboxylic acid. Now this is a really tricky question, so don't be too bummed if you didn't get it immediately. However, let's look at this. So if it's a mild oxidation reaction, we'll form the aldehyde, and if it's a strong oxidation reaction, we'll form the carboxylic acid. The reason why I said you need to remember your oxidants or reactants or catalysts that undergo oxidation is for this exact reason. Now, if we use dichromate, alcohols will undergo oxidation to form an aldehyde or butanone from butanol in this case. If you use permanganate, it will undergo a stronger oxidation and form butanoic acid from the original butanol. In this case, we used dichromate in the presence of an acid reflux. So thus, we're going to make the aldehyde here, which is going to be butanone. So last but not least, we can actually work out reagent X and E in the same step. So we know A and B. We know A, we know B, we know C is butanol of some kind, and we know D is butanone. We know it's a ketone because it undergoes mild oxidation, not strong oxidation. If it were to form strong oxidation, we'd form butanoic acid from butanol over here. Since it undergoes mild oxidation, we make butanone. So I'll write those down. Now, we need to find two more things. We need to find reagent X and we need to find E. If we look at B here, B again is 2-butene, and this A is also 1-butene. Both of those can undergo reaction with reagent X to form E, which is in the formula C4H9Br. Now, if we draw this thing out, we know there's a bromine here. So that's C4H9Br, right? This is an example of the alkene undergoing a halogenation reaction with bromine to form this bromoalkane here. So this is bromobutane, or if you want to be specific, 2-bromobutane. Now we found compound E, which is 2-bromobutane. Now we need to find reagent X, so we'll consult our mind map. Now if we look at the mind map, so we go from the alkene, which is 1-butene or 2-butene, and we want to form, that is, a haloalkene. Recall from the very first question that it doesn't always have to be a chloroalkane, it's just any haloalkane, right? So we want to form 2-bromobutane from this alkene here. It's going to be 1-butene or 2-butene. Now obviously this is the catalyst and this is the reagent. We're not using chloride, we're using bromine. So the reagent is going to be hydrogen bromide. So that's the final answer. The reagent X is hydrogen bromide. Don't write this here, that's the catalyst. So this is just a slide summarizing all our findings. So we know A and B are 1 and 2 butene respectively, doesn't matter the order. We know that compound C is butanol. We know compound D is butanone. And we know that compound E is 2-bromobutane. And we know that reagent X is hydrogen bromide. I'd like to pose 2 questions to you. So we know that 1 and 2 butene will react to form butan-2-ol. However, that's a fact that you've merely just accepted. Why can it not form 1-butanol? Similarly, A and B will undergo a halogenation reaction, or addition reaction rather, with hydrogen bromide here to form 2-bromobutane. Why not 1-bromobutane? So with these organic reaction questions, they actually combine a lot of the chemistry understanding you have into one complete question. So you get examined on the actual organic reaction pathway, you get examined on your ability to name and draw compounds, and you also get examined on the concepts that you've learned along the reaction pathways as well. This is an example of that type of question. So I propose to you, why do we make just 2-bromobutane? Why do we not make 1-bromobutane? And also, why do we make butan-2-ol and not butan-1-ol? The answer for this is Markovnikov's rule. You might remember that rule from our video on the introduction into this series. We explored that rule in a lot more depth there, but in the way of review, I will just revisit that. So on the left-hand side, we have 1-butene. And on the right-hand side, we have 2-butene. Now, both of these compounds will undergo addition with hydrogen bromide, which we found was reagent X in the in our mind map. And that's an addition reaction. Now, Markovnikov's rule says that when you have an alkene and you attach a functional hydrogen halide compound, it will undergo an addition. The hydrogen, you can remember, will attach to the carbon in the double bond, which already has the most amount of hydrogens already bonded. Now, this is this carbon here and this carbon here in both of these compounds. So the hydrogen is going to bond here and the hydrogen is going to bond here. That means the bromine is going to bond to this carbon and the bromine is going to bond to this carbon. Now, if we were to name both of these compounds, they would both be 2-bromobutane. Similarly, butan-2-ol kind of happens for a very similar reason. So instead of hydrogen bromide, we're basically having an addition reaction with water, or H2O. The H is going to go there. The H is going to go here. That means the OH, or the alcohol functional group, is going to go where the bromine previously would have, thus suiting Markovnikov's rule, and thus giving us butane 2-ol. Thus, 2-bromobutane and butane 2-ol are going to be the major products of these reactions. Before we get into the next question, I just want to bear in mind that these questions are usually going to be the most amount of marks in your chemistry exam. They'll usually test a lot of concepts that I touched on. So they'll test the organic reaction pathways, or your understanding of the organic reaction pathways. They'll test your ability to name and discern different compounds, as well as draw their structures. And they'll also be able to examine the concepts that you've learned along the way, such as Markovnikov's rule. It might seem like a lot of work that we're putting into each of these questions, but when they make up a 10th of your exam, they're pretty hefty. So in problem 4, we have a bit of a challenge. So firstly, we have to find a couple of things. We have to find the compounds for T, U, V, W, X, Y, and Z. We also need to find reagent P and Q. So we need to find a lot more things than we had previously. So the difficulty is stepping up a lot. However, with V, we can see that it's in this form here. When you do a lot of questions, you'll see that that is very akin to the molecular, or the empirical formula, for an alcohol. So an alcohol with 3 carbons is Propanol. So that gives us a start. Now we know that V is oxidized into U, which is then oxidized again into T, right? So we're off to a fairly good start here. Now we know Propanol undergoes a dehydration reaction with concentrated sulfuric acid to form W. We don't really know reagent P, right? We need to find that. However, we know that W isn't an alcohol. So that's probably an alkene of some kind, because it's in this formula, CnH2n. So that's going to be propene. So already off the bat, we know what 2 compounds are. So we know that V is propanol and W is propene, just by looking at some formulas. We need to know X now. So we can actually work out the molecular formula for X, or the name for X. So it's got 1, 2, 3 carbons. So we know it's got the prefix prop or something. We know it's got a chloro group. So this is a chloroalkane, right? So this is 2-chloro propane. Because it's got single bonds everywhere, and it's got a halogen in the second position. So we know 3 already just off the bat. Now, V and Y have the same molecular formula. They could be isotopes. They could be isomers. Sorry, not isotopes. However, we'll say propanol for now. And we know U and Z also have the same formulas. So if we find U, we'll find Z. So in effect, we've actually kind of limited, or off the bat, we've simplified this question. But this just goes to show, if you work systematically, and they've given you formulas, if you work systematically with them, and you get good at recognizing that that is the formula for an alcohol, right? So CnH2n plus 2O, if it's in that form, it's an alcohol straight away. We can actually get pretty good at solving these problems. We haven't even had to consult our mind map yet. Okay, so we started with the alcohol, which is compound V, and we know that's propanol. Compound V undergoes an oxidation reaction to form compound U, which undergoes another oxidation reaction to form compound T. Now, we've had a brief discussion on this before. You know that alcohols can undergo a strong oxidation reaction to form carboxylic acids straight off the bat. What I didn't tell you is they can form a weak oxidation reaction to first form an aldehyde, if you follow this amber arrow here. This can then undergo another oxidation reaction to form the carboxylic acid. So in effect, you can either form 2 weak oxidation reactions to get from an alcohol to a carboxylic acid, or you can skip the whole thing and form a strong oxidation reaction here, and get straight to the carboxylic acid depending on which of the reagents you use. Now, what I propose to you is, what's happening is compound V is propanol. That's the alcohol that we've started with. It was oxidized into the aldehyde propanol, which was then oxidized into the carboxylic acid, propanoic acid. Okay, so we know a couple of things. We know V is propanol, so I'll write that down. We know U is propanol, the aldehyde, and we know T is propanoic acid. As I said, V and Y have the same formula, so Y is also propanol, and Z and U have the same formula, so that is propanol. X was 2-chloro-propane, and W was propene. Now, we've done most of the question. We need two reagents. We've done all the formulas, so we can tick off this part here. We need the reagents. So we know we need the reagent P, which allows us to go from propene to 2-chloropropane, and we need reagent Q, which allows us to go from propanol to the aldehyde propanol. So we'll do those very quickly. So if we consult our mind map here, we have the alkene, and we want to form a chloroalkane here. So the reagents are these here. But the one they want, especially for the exam, so remember that's the catalyst, that's the one they want, hydrogen chloride. Now this is the diagram we had for working out the alcohol to the aldehyde to the carboxylic acid. We need a reagent, which will be our reagent Q, which takes us from the alcohol propanol to the aldehyde propanol. Now, that there is a mild or weak or still oxidation reaction. If you consult our table on the top right hand corner, a mild oxidation reaction occurs in the presence of potassium dichromate in a sulfuric acid reflux. So that's your answer for reaction Q. And this is just a summary slide highlighting all of those there. So with problem 5, I've changed it up a little. I've given you all of the intermediates that you need to get from these compounds, and I've given you some of these compounds because otherwise the question would be close to impossible. However, I've also added this question here, so you can have a practice of answering these exam style questions. So the top problem A, or the first part, would probably be worth 5 marks, so 1 for each, and then this part here would be worth 2 marks. So you should by now be getting good at correlating how many marks it's worth with how much information you need to provide. So if A is worth 5 marks and you need 5 things, it's 1 thing per mark. So if you get A and C, D, and E, and F right, you know that's 5 marks there. With B, it says to synthesize compound F in a lab, reflux is used. Justify its need. So why do we really need reflux? For 2 marks, you should be aiming to give about 3 concrete reasons. So if we're actually solving the question, let's work systematically. So to get from compound A, we use water in a dilute acid to form ethanol. So these type of reactions, they don't actually change the number of carbons we have. So we will know that ethanol has 2 carbons. So compound A is also going to have 2 carbons. So it's going to have eth something, right? We're off to a good start here. So if we consult our mind map, we can quickly find compound A. Okay, so we can work through this systematically now. So we have ethanol, so we'll start with compound A, and we know if compound A is reacted with water and this dilute acid here, which is phosphoric acid, we get ethanol. These reactants, or this type of reaction, isn't really going to change the number of carbons we have. So ethanol has 2 carbons, so compound A is also probably going to have 2 carbons as well. So we know it's going to have eth something, we just don't know what type of functional group it has, so we can consult our mind map to figure that out. If we look at our mind map, I've highlighted this exact reaction here. So alkenes undergo a hydrolysis reaction with the exact intermediates, water and phosphoric acid, to form our alcohol, which is going to be ethanol. So thus our original alkene is going to be ethene, which is compound A. So I'll just write ethene here. Done. We've done compound A. 1 mark. Next, we can see that ethanol is undergoing some kind of reaction to form compound D. You should be getting pretty good at recognizing what that is now. That's potassium permanganate. And this, going from ethanol to compound D, is probably an oxidation reaction. Now, we probably don't even need to consult our mind map now, so we should know this. So we know compound A is ethene. We've worked that out. We know ethanol. We know this is going to be an oxidation reaction. So compound D is probably going to be ethanoic acid. If you still don't feel confident, I'd recommend pulling up the mind map and then consulting and confirming that. You'll find that in the initial mind map that we posted. But compound D is indeed ethanoic acid. Now we can start on the right hand side here. So we have compound C, and it undergoes what's probably going to be an addition reaction to form 1-chloropropane, right? If we consult our mind map, the only thing that undergoes an addition reaction in the presence of hydrogen chloride is an alkene. So we know that compound C is probably going to be an alkene of some kind. So it's going to be ene as a suffix, right? We have 1-chloropropane. So we know it's going to have the prefix prop. Combine those, compound C is probably going to be propene. Now, to find compound E, we know that the haloalkane is undergoing a reaction with sodium hydroxide. So we can consult our mind map here. So we have the haloalkane here, or the chloroalkane rather. In the presence of sodium hydroxide, it's going to form an alcohol of some kind. So we know that compound E is probably going to be propanol. And this is just a quick summary slide showing all of these answers. However, we're not done yet. So it's asked for 5 things. We found 4, A, C, E, and D. We didn't read the question properly. We still need to find compound F. So if you read the question properly, it said that at the very end, 2 reaction pathways are presented that yield the final compounds D and E. Compounds D and E are then heated under reflux with concentrated sulfuric acid to form compound F. So we have ethanoic acid and propanol under reflux to give us what is going to be, hopefully you got it, an ester of some kind. So this is that exact reaction taking place between propanol and ethanoic acid. So I'll add a plus there. In the presence of a acid reflux, we get the ester propyl ethanoate. If you're still confused on how to name esters, I recommend you go back to a video on naming the naming conventions of each of the functional groups, where we went into that in a little more detail. However, this is propyl ethanoate, the ester, which is compound F. So we've done all of them, and we've got one more part of the question left. So in part B of problem 5, we were asked to justify the need for acid reflux, especially when we're making esters. Now, I recommend with all of your answers in chemistry, especially with these 2 markers and 3 markers, you answer them systematically. So, first, just give a general rationale into the actual principle. So, reaction rates, increase temperature. So, all of your questions, you should be approaching with a plan. My plan is, I'm setting some context as to why we need an increase in temperature in the first place, right? Next, we have an issue. If we increase the temperature, carboxylic acids, and especially alcohols, are particularly quite volatile, meaning that if we increase the temperature, they'll form a vapor and they'll escape. And that's exactly what I say. If we increase the temperature, alcohols and carboxylic acids, especially alcohols, are quite volatile. They'll escape as vapors. That increase in temperature, or that increase in reaction rate we get with that increase in temperature, is useless because we have no alcohol left to react with. All of it's become a vapor. Reflux gives us the advantage of allowing us to increase the reaction rate without losing or any of that alcohol escaping into the atmosphere as a vapor. So thus, reflux solves the problem, and that would get you all the marks. So hopefully you've learned a thing or two about organic reaction pathways and how to actually answer these questions. It is a lot of information to take in, so I completely understand if it felt like an overload, but just know these questions tend to be quite hefty. So 9, 10, I've seen it, sometimes 11 or 12 marks offered for these questions, and they usually examine a lot of the principles. For an exam situation, I'd recommend not memorizing, but practicing a lot of these questions, because hopefully, as you can see, when you do a lot of these questions, you get good at answering them and remembering the reactants and what type of reactions you get. And also, if you're stuck, just use the mind map as you're studying. And hopefully, as you do more and more questions, try leaning away from using the mind map more and more.